we deal with, again, these kind of systems. We have coupled loops, and dynamics can be time-varying, nonlinear, and uncertain. And also, due to different, damages, sudden changes, we can have those due to reconfiguration, deployment of a payload, or damage. And also, these uncertainty, that can be uncertainties based on the disturbances, unknown disturbances. Standard adaptive control architectures are based on standard Lyapunov theory, so they assume that existence of constant unknown ideal set of weights, which is fine for most applications, but sometimes they might require for performance recovery unrealistically high adaptation gains or learning rates. This is dangerous from the practical standpoint because it can excite unmodeled dynamics and also can result in excessive amount of control activity. So, due to this, they may fail to achieve a desired performance under failure recovery. Also, since we have unstructured uncertainties, they require modifications. Otherwise, when we have measurement noise or so on and so forth, they can burst, basically. So, we need modifications. So here, the goal of this talk is to develop a new adaptive control architecture that preserves stability and achieves desired performance. And we don't want to use so much high adaptation gain, and I will try to relax the assumption of constant ideal weights. Basically, we are going to allow time variation in the ideal weights such that fast variation is allowed. And this variation can be discontinuous as well. And this architecture will be advantageous for systems with sudden change in dynamics, and different than standard adaptive control architectures, we don't need modifications for uniform ultimate boundedness. Okay, now, I need to make a point clear. We can still add modifications for improving robustness, but for uniform ultimate boundedness, we don't need modifications. So, we all mainly talk about that system, uncertainty, ideal reference model, nominal controller, weight update law, and adaptive control signal. So once again, I will say that A and B is unknown and controllable, and here X is available for full state feedback. And tomorrow I will also talk about output feedback derivative-free adaptive control. So here, delta of X of T unknown makes uncertainty in the classical sense, and this is the classical uncertainty parametrizations. In order to handle time variations or state-dependent unstructured uncertainties, we need to assume that we also have additional residual error. And beta of X is a known basis. If it is unknown, again, just you can use neural networks as Gestalt, so without loss of generality. So here again, I will stick with the same reference system. Reference command AM is Hurwitz because we want our reference system to be stable. And here, since R is bounded, reference command, we can say XM is uniformly bounded for all initial conditions. So again, I will stick with the same nominal controller. The feedback part, the feed-forward part. Here I don't use the minus sign, so that's why we have a plus here. If you put here minus, then it becomes minus. So I just wanted to mention about this notation. So again, this is the standard adaptive controller, and this is the standard weight update law. Since we have residual error, then we need to use sigma modification, E modification, or projection operator. And this is the Lyapunov equation. And then at morning, I proved that by considering this inertia function, we have uniform ultimate boundedness. We discussed matrix adaptation gain. Here I am using scalar adaptation gain. Actually, it doesn't make a big difference. So, if we want to extend this from this assumption to this relaxation, we need a different weight update law. in order to handle this continuous variation in the ideal weight. So the question is, do we have a better alternative for this purpose? So now we are going to start the derivative-free model reference adaptive control, and these are a bunch of papers, journal papers, conference papers that we included in your flash drive. So basically, I am going to talk about a summary of these 4 in this talk, including flight test results, and tomorrow I am going to talk about output feedback, derivative-free output feedback architectures. So now, we have a new uncertainty parametrization. So here, this is unknown, time varying. It is a bounded weight. We are assuming it is bounded, but I don't assume anything about its time rate of change. It can represent sudden change in dynamics, discontinuous variations, and so on and so forth. Here, this epsilon star, basically epsilon star comes from this residual error upper bound is 0, because it can be justified, because now we allow time variations in the weight matrix. So due to this fact, we don't need to assume that residual error, existence of the residual error. It can handle these kind of unstructured uncertainties. So here we have again the known basis. Now a couple of remarks regarding this parametrization. First of all, this expands, it definitely expands the class of uncertainties that can be represented by given basis functions due to the inclusion of time variation. So this is the first difference. And also an adaptive law subject to this relaxation can be more effective in canceling a wider class of uncertainties, basically what I mean by time varying uncertainties that can be changed rapidly. And again, once again, this does not place any restrictions on the time derivative of W of t. It may not be differentiable, it can vary infinitely fast, and we don't have any assumption on the time derivative of W of t. So now, that's the first theorem for the derivative-free architecture. For this system, for this relaxed assumption, for this ideal system, for this again, the nominal controller augmented with the adaptive controller. So this is the form of the derivative-free weight update law. Actually, you can call it also integrator-free. The reason we call derivative-free, we don't have that. So basically, it uses omega-2 hat has the current information of the error. So it uses the past information of the weights to improve the performance, and also current information comes from the error signal simultaneously. So here tau, which looks like a time delay parameter, it is not now. It is a harmless design parameter which has an effect on the transient bounds and steady state bounds. We are going to discuss about that. Omega-1 basically, if you think like that, let's say scalar, if this scalar we can write it that if this design parameter satisfies this bound. So omega-2 has this form here. Kappa 2 is the new adaptation learning rate. So first design parameter, second design parameter, and third design parameter. So we are going to discuss the effect of all these design parameters to the system performance. So first of all, we have uniform ultimate boundedness of the error dynamics, and W hat weight estimation error with this weight update law. And the proof, I would like to go through the proof, but the proof is, if I'm not wrong, 4 pages long. And I don't want to bore you about that, but just a sketch of the proof is we consider these Lyapunov-Krasovskii functionals. So now we have an integral here. So once we take the directional derivative of this energy function, then we have these upper bounds. Basically, similar to what we talked about on the uniform ultimate boundedness, basically, if error is bigger than this, basically, it again comes from C1D. Basically, they are depending on the Q matrix from the Lyapunov equation, P matrix. So outside some set, V dot is negative definite. So that's why it follows that the error estimation error and the weight estimation error are uniformly ultimately bounded. So I have a couple of remarks. So we were talking about this previously. Now, if we simply take first order error integration with a step size of tau s, then we can write a law which is very similar to derivative-free law. Now, it is nice because we always implement adaptive laws like that. So this is a nice connection. This form is identical to the DF-MRAC only if omega is identity. Of course, that selection is not permitted in the derivative-free MRAC. Kappa 2 selected like gamma tau s, and also if we select the tau of design parameter, time delay design parameter of the derivative-free to be same as the sampling time. Of course, if we do that, then they are equivalent, otherwise not. Again, omega 1 identity is not permitted in DF-MRAC. Tau is not necessarily equal to tau s, and in omega 1 basically again satisfies these conditions. So here we talk about uniform ultimate boundedness, and we didn't mention about the modification term because it does not require any modification term to prove UUV. For robustness, again, we can include. So it is capable of handling unknown disturbances, time variation in system matrices. So we have a bunch of design parameters. Tau here, P here, CR, convergence. So tau again P this. P1 and P2 basically are based on, they have parameters coming from the other two design parameters, omega 1 and kappa 2. So all design parameters embedded in these two expressions. So what are they? The first is uniform ultimate bound estimate, meaning I am starting from here, I am converging to some set, and I am staying in that set. So this is the uniform ultimate bound. Like, more clearly, let's say E time. So this is the R, uniform ultimate bound estimate. So I start somewhere, I am reaching that set, and I won't leave that set because outside V dot is negative. Now we also have an additional design parameter. We can adjust the convergence rate. So basically what I mean by convergence rate is how far it reaches to this ultimate bound, tau star. So we can control the convergence rate of derivative-free law, and also we can control the size of this ultimate bound. So we have, this is basically, it can be analytically tuned other than using ad hoc approaches. So increasing tau here increases the convergence rate, but when you look at distribution, also it slightly increases the ultimate bound. So it is a trade-off. So if you increase tau, basically you need to make this small by adjusting your adaptation gain and omega 1. So now, what happens if we have that? Okay, we are relaxing an assumption, but standard MRAC, when the weights are constant, has asymptotic stability, right? So now we should be able to recover asymptotic stability with DF-MRAC for the case of constant ideal weights. If the ideal weights are constant, then the derivative-free weight update law becomes this. Then here, omega 2 hat is the same, tau is the same. We don't have an additional design parameter here. Then error basically goes to 0, ST goes to infinity, and the uncertainty, the difference between the actual uncertainty and the estimated uncertainty becomes 0. So we again recover the asymptotic stability of the error dynamics for the case of constant ideal weights. And the proof basically follows from the main theorem. So we just need to replace time variation in weight with the constant weights, and we need to choose omega 1 to be identity, which is the only parameter choice if the ideal weights are constant. Otherwise, we need to select it like that and then apply it ourselves. Now, up to now, we didn't discuss much that the case, even for the MRAC case, when we have uncertainty in the control effectiveness, because it is common that we have uncertainty. So let's say we have a scalar system, okay? Let's say we have applied our control action to some actuator. Here I am neglecting actuator dynamics. Professor Johnson will going to cover that. So in this case, since we have single input, let's say our actuator is performing well, then let's say its performance is degraded by 50%. Then this lambda is scalar for single input systems, then its nominal value is 1, and when we have 50% reduction in the control effectiveness, its uncertain value becomes 0.5. So it is of common practice to say that we need to handle this kind of uncertainty. It's a derivative-free weight update law, assuming that this is invertible, and slightly relaxed conditions, slightly relaxed version, if you have these that which allow some of the control effectiveness components to be 0, so then if this is the case, this is the weight update law. So you have 3 possibilities. Okay, so let's do more interesting stuff than math. So now we are going to see some one simple example on a scalar system, one high fidelity example, and we are going to see one flight test result. So for the simplest case, just to illustrate derivative-free adaptive control, I will assume this rolling dynamics. Here x is the basic roll rate, u is this aileron diffraction. It is basically an overly simplified model. Here w scalar, everything is scalar. These parameters are also scalar. Time varying ideal weight. And of course, aircraft dynamics do not behave in this manner, but we can use this example still because their stability derivatives can go a sudden change. So here I choose this reference system, and we are going to compare MRAC as its pure form with the derivative-free adaptive control. So first of all, we select this uncertain ideal weight, time varying ideal weight to be this red. So it is basically a not quite sinusoidal, but it is a chirp signal changing from different frequency component to different components. So since we are applying here nominal controller, no adaptation, estimated weight is 0. This is the control signal, so this is the performance. This is the performance when we turn on adaptation in the sense of classical MRAC. So since the ideal weights are time varying, it performs like that for an adaptation gain of 100. So it performs much better if we go 10 to the power of 4, which is a very high adaptation gain. So you will see the effect of bursting actually in the control history. So now this is the derivative-free adaptive controller. It estimates even this weird change in the ideal weight. So one more extreme case, of course, now here I will, just for the illustration purposes, assume that uncertain time varying ideal weights is a white noise. So which is really an extreme case. So let's say my weight is behaving like this. So this is the nominal response. So this is what happens when we apply the derivative-free controller. Basically, all I want to illustrate is the ideal weights are very closely estimated. So this is just an expanded view of the estimate of white noise. Now, one more thing I would like to mention. Now, standard adaptive controllers has an integral action. And also, in addition to that, if we use a nominal PI controller with the integration-based model reference adaptive control, then we can have too much integral effect. And from the classical classical robustness standpoint, if you have more integral effect, basically your margins gets lower and lower. So here is the case. This is the model reference adaptive control. Baseline is PI. So this is the case of 20 adaptation gain, and the black dotted line is 200. These oscillations and the control signal, and here is the delta is the actual uncertainty. We use the estimation of it by 20 of MRAC, and this is an adaptation gain of 200. This is a scalar system, so the performance here is nice, but during the transient time we have this overshoot due to having too much integral effect. Integral from the adaptation, integral from the PI baseline controller. So this is the case when we have derivative-free adaptive controller. Since it is derivative-free, not integral, like not harsh as standard adaptive controller. So when we augment these two controllers together, basically it does a much better job than the standard MRAC. So this is the case. Now I included that I changed B matrix to 0.1. But all I meant was this lambda is now 0.1, and due to this fact, this is derivative-free performance. But since we didn't add the additional two weight update laws, it performs like kind of weird. So if we, in addition to the this one weight update law, if we turn on the other two laws, or if we use this law, basically we have a much better performance. So this is the importance of including the other weight update laws or using this law if we have uncertainty in the control effectiveness matrix. So I also wanted to revisit WinRAC dynamics, since this is my universal example for this workshop. You remember, this is the morning's first presentation, the last slide, so we have this performance. So I also included a code for the derivative free so that you can tune omega 1, kappa 2, and tau. So this is the how weight update law is implemented. Basically, this is the response when we have derivative free adaptive controller is on. And here I choose the design parameters. And you can take the code, just play with the code, see what happens. Now, let's look, after all these simple examples, let's look at a high fidelity model. Basically, this model is developed by NASA Langley Research Center, and it is a really high fidelity scale transport aircraft model. Basically, non-linear aircraft is modeled. It has two left, two right elevator controls, aileron, rudder, spoiler, stabilizer, thrust controllers. And in order to get the model that we know, or to design the reference system, we linearize that model at an angle of attack of 2 degrees and 10 feet altitudes. And here the primary sources of uncertainty, basically NASA modeled these kind of uncertainties and gave us, if my memory is correct, 6 damage cases. So in this presentation, I am going to talk about 2 harsher damage cases, 2 the hardest damage cases that we can handle with derivative-free adaptive controller. So nominal controller, basically, as I mentioned, we are going to augment a robust controller with the adaptive controller. So we used robust servo mechanism LQR. Basically, it has an integral action, and it's a state feedback controller. We like tracking of roll, pitch, and yaw rate commands. And for the simulation, we only consider roll and pitch rate command tracking. So when everything is perfect, no uncertainties, no adaptation. So this is the roll rate response, this is the pitch rate response, yaw rate, angle of attack, sleep, and elevator, aileron, rudder, spoiler. Basically, adaptive controller uses that. So everything is ideally should look like this without any uncertainties. So for the adaptive controller, as I said, we are going to marry derivative-free adaptive control with the alarm modification, performance plus robustness, and these are how we tune design parameters. And also, I should say, I started developing adaptive controllers with Tony Callis, Professor Callis, before we came up with derivative-free idea. So the standard that we tuned our best, we put a lot of efforts to make standard adaptive controller to perform as nice as possible. That's why you have these magical parameters here. We tried to tune it so well. So then we came up with derivative-free, then we applied that. So the standard adaptive control response I am going to show is tuned up to the best possible case. So we tuned hard to make it look very nice. Same here coming from the Lyapunov-Krasovskii, we use the same basis reference model, and we are using neural networks here. And we are going to consider two hardest damage cases. The first one is left outboard flap is off. Basically, here left outboard trailing edge flap is missing. And the second case is left wing tip off. What I mean by that is 25% loss of outboard left wing tip, and also left aileron is missing. So here is the nominal control response. I will just consider here and here for the missing left wing tip case. Nominal control behaves like that. So here is the derivative-free adaptive control without ALR. If you look at the scales, it comes up to 30. Here the scale is 10, so it is a much better performance. And it is not a toy example, so that's why you have this. This is the best we get with the derivative-free response without adaptive loop recovery. So now, again, missing left, this is how MRAC performs. So we could not able to get rid of these oscillations, even though we also tried a couple of modifications. And as Girish mentioned, sigma modification didn't work well for this example. So now, more harsher design case, missing vertical tail case. And this is a nominal control response, basically behaving, basically aircraft crashes. So this is the derivative-free adaptive control response without ALR, which basically performs very well. And this is the response with the MRAC. You know, since Dr. Callis was my advisor during the PhD, he pushed me to get a very nice, like, we tried to understand why MRAC doesn't do well, but we couldn't get a stabilizing solution with MRAC. We couldn't able to stabilize the system with MRAC. So this is the derivative-free, this is the classical MRAC case. So now, this is again derivative-free without ALR. So why we have oscillations? Because we now, in addition to this harsher case, we inserted 0.1 seconds of time delay into the right aileron. So once we turn on the ALR, basically, again, we can able to recover time delay. Basically, now the system outperforms when we compare it with the previous slide. Now, flight test results. So this is the aircraft, AirSTAR. So the high fidelity simulations that I showed you, basically a model of this aircraft. So basically, this flight test is performed in collaboration with NASA. Basically, we designed our controller, then we sent to them, so they implemented our controller, and we got nice results. So in addition to what we did for the high fidelity model, here we added washout filter to the baseline design in the yaw rate feedback to the rudder pad, and in-flight damage, of course, they didn't damage the airplane. So basically, they represented the in-flight damage by introducing feedback loops to change the stability derivatives of the system. And also, there are basically sources are unknown destabilizing changes in stiffness and damping terms in the longitudinal and lateral dynamics. And once again, we implemented derivative-free with ALR. So this is the example of first flight test result. In this slide and in the following slides, you will see all four figures, basically red dashed lines here and here, basically pilot comments or auto-generated comments from the ground station. Blues are basically aircraft response, actual aircraft response. This is for roll rate, this is for pitch rate. These are for baseline controller, and these are for adaptive controller. So roll rate, peak rate for baseline and for the adaptive. So they are basically kind of the same. I try to make the scales the same. So, you know, for these kind of profiles, so when there is no uncertainty, roll and peak rates look nearly the same, which we should expect because there is no error. However, due to the modeling error, most likely due to the cross-axis coupling, even though we don't have uncertainty, derivative-free adaptive controller improves the performance in the peak rate. So this is the nominal control, baseline control, and this is how derivative-free performs. So actually there is some modeling error due to the cross-axis coupling. So derivative-free improves the performance. I'm almost done. So this is the latency emulation. Basically, they apply time delay to the derivative-free and to the baseline to the derivative-free up to basically they increase time delay up to 0.1 seconds. Both controllers blow up here, so basically that means derivative-free the alarm modification has the same time delay margin as the nominal system, and this is the baseline response under a pitch stillness and roll ramping reduction of 50% and plus 0.2 under pitch rate command. So this is the improvement with derivative-free controller, then the baseline. Again, improvement in here, and in here I'm slightly going fast because I'm out of time. And here again, another improvement. So basically I can say adaptive controller improves the tracking error by at least a factor of 2. And that's it. Basically, I tried to show a better alternative to standard MRAC for the case when we have time variation in the weights. And the proof lies, instead of using Lyapunov function, energy function, we are using Lyapunov-Krasovskii functionals. And we also analyzed how the design parameters influence uniform boundedness and also the exponential rate of convergence.